All right, so we are doing problems from chapter 16. Okay, so this problem says express the displacement current in a capacitor in terms of the capacitance and rate of charge change of the voltage across the capacitor. Okay, so let me remind you what the displacement current is. Okay, so here's the Maxwell's equations. See, this is current density. Moving charges produce magnetic fields. And look at this. This acts like a current as well. So this term is similar to that. Okay, so time varying electric fields act like displacement. So epsilon naught times del E by del T, this is displacement current. Okay. So here's a capacitor that is being charged, and as it's being charged, the electric field between the plates changes, and so the displacement current is epsilon naught del E by del T. Okay. Epsilon naught. Okay. the electric field between the plates is V over D, okay, volt per meter, and so del E by del T is 1 over D times del V by del T, okay, and the voltage, so voltage is, and for a capacitor, okay. All right, so 1 over so the displacement current is epsilon naught times 1 over D del V by del T. Okay, so what do they want us to do? Express the displacement current in a capacitor in terms of the capacitance and rate of change of voltage. So all right, so we want to express this in terms of capacitance. Capacitance is epsilon naught area divided by D. So capacitance over area is equal to epsilon naught by D. So the displacement current is capacitance over A del V by del T. All right, and that's what they want us to do. Express the displacement current in terms of the capacitance and the rate of change of voltage across the capacitor. Yeah. All right, so here's an example. So here's a capacitor. You're charging it. The potential difference, Vt between the plate shown above, is instantaneously increasing at the rate of 10 to the 7 volts per meter. What is the displacement current? So you just saw that the displacement current is capacitance divided by area times del V by del T. They give you the rate of change of voltage, okay? And the displacement current is, this works out to epsilon naught by D del V by del T. And they tell you the separation on the plate is 1 centimeter, and the area of the plate, okay, so the area of the plate is that. Okay, so we don't even need the area of the plate. So the displacement current is epsilon naught is 8.85 into 10 minus 12. Epsilon naught is Coulomb square, Newton meter square. 1 centimeter. And this is 10 to the 7 volts per second. And this is a current, so all this will work out to be amperes. So this is 10 to the minus 5, 10 to the minus 3. So 8.85 into 10 to the minus 3 amperes. So 9 milliamperes. Yep. This problem says that if electric and magnetic field strength varies sinusoidally in time at a frequency of 1 gigahertz, so the frequency is 1 gigahertz, being 0 at t equal to 0, then, so there's a functional form. F is 1 gigahertz, the frequency is 1 gigahertz, and B naught is given by that. When are the field strength next equal to 0? Okay, so I'll just draw the electric field. So the electric field as a function of time is varying sinusoidally. Okay, it's 0 at time 0, and then it's 0 when this is equal to pi. Okay, so the next 0 happens when 2 pi f 0 at 2 pi f t equal to pi. So t equal to 1 over 2f. So at that time, and by the way, it's so yeah, so 1 over 2 times the frequency is 10 to the 9 hertz. Hertz is 1 over second, so 0.5 into 10 minus 9 seconds at 0.5 nanoseconds. Yep. When do they reach their most negative value? So this was 0, and they'll reach most negative value at 3 pi by 2. So this is pi by 2, pi, 3 pi by 2. So 2 pi ft equal to 3 pi by 2. And so t equal to 3 over 4f. And again, f is a gigahertz, so that gives you the 10 minus 9, and 3/4 is 0.75 nanoseconds. Okay. So how much time is needed for them to complete one cycle? So this will equal one complete cycle is, there's one complete cycle. And so this quantity is equal to 2 pi. So one complete cycle and that is called the period. So the period is 1 nanosecond. So again, this is showing you the electric field, which is a sinusoidal function. There's the sinusoidal function. So this problem says a radio station broadcasts at a frequency of 760 kilohertz at a receiver some distance from the antenna. The maximum magnetic fields of the electromagnetic wave is detected to be 10 to the minus 11 Tesla. The magnetic field in this room is 10 to the minus 5 Tesla roughly, so that's 1,000,000 times weaker. The magnetic field of this wave, in the wave. Okay. You guys have seen those circular antennas? Okay, so you have seen antennas like, there are two types of antennas. I mean, this is back in the day when you used to catch TV signals like this, and then you would see circular antennas like that. This guy detects the electric field, this guy detects the magnetic field. So as the magnetic field here changes, it induces a current in this antenna. In this guy, the electric field induces a current in the antenna. Okay. So anyway, so you can catch this signal detecting the electric field or the magnetic field. So there's this, the amplitude of the magnetic field is that. What is the maximum electric field? And you saw that in any electric field, the ratio of the electric field to magnetic field is C. So E max is C times B max. And so 6.3 into 10 to the minus 3, and electric field is volts per meter. So that's the amplitude of the electric field. Yes, C is a constant. C is the speed of light. And what is the wavelength of the electromagnetic field? So C is frequency times wavelength. Wavelength is C divided by. Again, hertz is 1/2. So, and this wavelength works out to okay, so okay, that's 3 times 10 to the 5, and so this works out to 394.7 meters. So the wavelength is about 0.5 kilometer. So roughly from here to Mainland High School. That's the wavelength. Okay, this problem says, at what distance does a 100-watt light bulb produce the same intensity of light as a 75-watt light bulb produces 10 meters away? So this bulb at 10 meters away produces a certain intensity. A 100-watt light bulb will produce the same intensity at a further distance. Okay, so intensity is the energy passing per unit time per unit area. Okay, and the intensity is given by, this is power, and so that is power divided by area, and this that light is emitted equally in all area, and the area, surface area of a sphere is 4 pi r squared. Okay, so what we want is the 75 watt power and 4 pi 75 square should equal the 100 watt power. Yeah. Hundred watts divided by 75 watts. Okay. So R100 divided by R75 equal to square root of 100 divided by 5. 70. $11.5 meters. All right, so a 100 watt bulb will produce at 11.5 meters the same intensity of light that a 75 watt bulb will produce at 10 meters. So, so this problem says a small helium neon laser has a power output of 2.5 milliwatts. The lasers that you can go buy at a little store, that's 2.5 milliwatts. What is the electromagnetic energy in a 1 meter length of the beam? Okay. So this is 1 meter long. Okay, so in 1 second, milliwatts, so power is energy divided by time. Energy is power times time. Okay, so in 1 second, the length of the beam would be equal to c meters. Okay, and so the energy content in 1 second, so the energy content of 2.5 milliwatts times 1 second is, and the length is equal to c, is 2.5 millijoules. So this beam of light, this length of the beam contains 2.5 millijoules of energy. And you want to find what is the energy content of 1 meter, so you divide that by c. So energy content of 1 meter is the energy content of that divided by c. 2.5 millijoules divided by 3 times 10 to the 8 meters. That's the length of this beam. So this is equal to .833 into 10 to the minus 11 joules. That's 10 to the minus 8, and then a milli is 10 to the minus 3, so that's 10 to the minus 11. And so this is equal to 8.33 into 10 minus 12 joules. So 1 meter of that beam will contain that. Okay, so this laser that I have, oh, this is 5 milliwatts. So 1 meter of this beam will contain 16 times 10 to the minus 12 joules of energy. That's what that means. Okay? So, and this is relevant if you shine this light and energy is absorbed, how much energy is absorbed. Okay? So when you get cataract surgery, when you know, what is that surgery called where they're changing your, oh yeah, LASIK surgery. So they peel your cornea back and they burn cells, and they're burning cells using lasers. So you need to know how much energy is being deposited. So this problem says, at the top of the Earth's atmosphere, the time average Poynting vector associated with sunlight has a magnitude of 1400 watt per meter squared. So the intensity is that. Okay. Intensity is 1400 watts per meter squared. Okay. And the intensity is S average, which is E max V max divided by 2 mu naught. Okay, so this is the intensity of sunlight above the Earth's atmosphere. So here the Earth, there the atmosphere. So what that number tells you is every meter square, enough sunlight is falling for every meter square. It's like 14 100 watt bulbs are shining. And then by the time it gets to the Earth's surface, it's half of it is reflected. So 700 watts per meter square is reaching the surface of the Earth. Okay. What are the maximum values of the electric and magnetic fields for a wave of this intensity? So they want us to find E max and B max. Okay. So S average is that E max, and B max, remember E over B is C, and so B is E over C, so E max over 2 mu naught C. So you can express this in terms of B max is E over C, so I made that E squared, and there's the C. So E max is 2 mu naught C times S average, square root of that. Mu naught is Tesla meter per amp. C is 3 into 10 to the 8 meters per second. And S is 1400 watts per meter squared. All right, so let's, that makes it 10 to the 1, okay? And we'll take 10 to the 3 here, so you get 10 to the 2. So E max equal to 10 to the 2 volt per meter, and the stuff inside the square root is 8 pi times 3 times 1.4. Okay, so 1030 volts per meter. That is the amplitude of the electric field in sunlight, when it reaches Earth. And B max, of course, is just E max divided by C. And so this is 1030 volt per meter divided by 3 into 10 to the power 8 meters per second. And that will work out in Teslas. So okay, so this is roughly the strength of the Earth's magnetic field. Okay? So half a Gauss. No, this is 1/10 the strength of the Earth's magnetic field. Okay. Then they say, what is the total power radiated by the sun? Assume that the Earth is 1.5 times 10 to the 11 meters from the sun. And the sunlight is composed of electromagnetic plane waves. All right, so here's the sun, and the Earth is at distance r. So intensity reaching the Earth, intensity is this guy. Is power of the sun divided by the surface area, 4 pi r squared. So the power of the sun is 4 pi r squared times the intensity, 4 pi 1.5 into 10 to the 11 meters square, and intensity is 1400 watts per meter squared. Okay. So this meter squared will cancel with that, and so you'll get the power of the sun in watts. Okay, so this is equal to 4 pi into 1.5 square into 1.4 into, that's 10 to the 22 plus 3, 10 to the 25. Okay, let's write it like this. This is, we'll borrow 100 from here. So this is 3.96 into 10 to the 24 into 100 watts. Okay, so this is 4 trillion 100-watt bulbs. So the power of the sun is 4 trillion 100-watt bulbs. Yeah, that's how bright the sun shines. So this problem says a 2.5 diameter university communication satellite dish receives TV signals that have a maximum electric field strength of, so there's a dish outside this building, okay, so that receives a signal. The electric field strength is 7.5 microvolt per meter. What is the intensity of this wave? So the intensity of this wave is S average E max. You saw that it's E max squared 2 mu naught C. Okay. So the intensity would be E max is 7.5 microvolts. And mu naught is 4 pi times 10 to the minus 7 Tesla meter amp, and C is 3 times 10 to the 8 meters per second. All right, so this will make 10, so that will make that 30, 8 pi times 30, and this is equal to, in the numerator you have 7.5 square into 10 to the power minus 12, and this is intensity, so it'll be watts per meter square, and in the denominator you have 8 pi into 30. All right, so this intensity will work out too. So 74.6 into 10 to the minus 15 watts per meter square. Okay, you saw that intensity of the sunlight reaching Earth is 1.4 times 10 to the minus, 10 to the power 3 watt per meter square. Okay, so the satellite, the intensity of the beam reaching the satellite dish is 10 to the power 18 times weaker. And we catch that signal and amplify it. So, yeah. So sunlight, well, the intensity of sunlight is quite large. So what is the power received by the antenna? So the intensity is power divided by area. So power is intensity times the area of the dish, and they give you the dish has a diameter of 2.5 meters. Okay. So, by the way, the dish is parabolic, and then it'll receive light and then focus it to a receiver. Yeah. And they tell you this diameter, this is 2.5 meter diameter. Okay, so, and that's the, so the area is, what the relevant area is the area of that circle. Okay. And that's the diameter. So the power received by the antenna is intensity times pi d squared by 4. We just calculated the intensity. The intensity was 74.6 into 10 to the minus 15 watts per meter square. Pi by 4, 2.5 meters square. So the meter square will cancel with that, and that you'll get that in watts. So this is equal to so 366.2 into 10 to the minus 15 watts. So that big antenna, so the antenna is as big as this table, and that's only getting 10 to the minus 15 watts, okay, or 10 to the minus 12 watts. And then you have to amplify that signal and then extract information from it. Okay, so what is the power received by the antenna? If the orbiting satellite broadcasts uniformly over an area of that much, a large fraction of North America, how much power does it radiate? Okay, so here's the orbiting satellite, and that's radiating this power over that area. Okay, and you just saw that the power received by this area. Okay, so the power radiated by that, so power radiated by the satellite is power received by the antenna times times this total area divided by the area of the antenna. Total area divided by the area of the antenna. Okay, this tells you how many antennas are there. So the power received by each antenna times the number of antennas gives you the power radiated by the satellite. Okay. So power radiated by the satellite is power received by the antenna. This is here's the power received by the antenna. 366.2 into 10 to the minus 15 watts. The area over which this is radiated is that 1.5 times 10 to the 13 meters square. And the area of each antenna is pi over 4, 2.5 meters square. So essentially that's how many antennas you have. Okay, let me calculate that. That is the power received by each antenna. Okay, so it's essentially 3 trillion antennas you could cover. That's how much area the signal is coming to. All right, so the power of the satellite is then equal to that's pretty amazing. Just 1 watt. Wow, that is pretty amazing. Yeah. All right, this says a microscopic spherical dust particle of radius 2 micrometer and a mass of 10 microgram is moving in outer space at a constant speed of 30 centimeters per second. A wave of light strikes it from the opposite direction of its motion and gets absorbed. Okay, so here's a light beam that is hitting a, this is going at 30 centimeters per second. Okay. So light beam hits it, and the light beam is absorbed. Remember, light beam exerts a pressure, okay, and so pressure times area is the force on it, and it'll stop this particle, okay, and gets absorbed. Assume the particle decelerates uniformly to zero speed in 1 second. What is the average electric field amplitude in the light? So they're asking you what is the, how strong is, what is the intensity of this beam, which is related to the electric field strength. Okay. So the acceleration of this thing is, okay. So this guy gets stopped in 1 second. So V is V naught plus AT. Acceleration is V minus V naught. Okay, so here the initial velocity of this is V naught. Okay, we'll make that V naught. The initial velocity of the particle is 30 centimeters a second. The final velocity is 0. You're stopping it. And 0.3 meters per second divided by 1 second. So the acceleration of the particle is negative 0.3 meters per second squared. The negative sign just telling you that the acceleration is in that direction if this guy is positive. Okay, so the force on this guy is the mass times his acceleration, and the force is pressure, and the force is exerted by this light beam, which is pressure times the area of cross section. Pressure times the area of cross section. So mass times acceleration is, and the pressure, you guys here, let me show you the expression for pressure. It's the intensity divided by the speed of light. So light beam exerts pressure. Here's the pressure exerted by a beam of light that is absorbed. Okay, so it's intensity divided by S average divided by C times pi r squared, where r is the radius of that thing. All right, so this is an S average is equal to E max So they're asking for the electric field amplitude. We'll express this in terms of the electric field amplitude is 2 mu naught C times pi r squared. All right, so you see, we know the mass of the particle, we calculated the acceleration of the particle, we know the speed of light, and we know the radius of this particle. So we know that, and that. So Emax is the only unknown. So the amplitude of the electric field in the light beam that is stopping this particle is ma times 2 mu naught c squared divided by pi r squared. So now we'll calculate all of this. All right, so the mass of the particle is 10 microgram. Micro is 10 to the minus 6, and a gram is 10 to the minus 3 kgs. So that's 10 to the minus 9, 10 times 10 to the minus 9 kgs. So the mass is 10 times 10 to the minus 9 kgs. The acceleration is 0.3 meters per second square. 2 mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. C, the speed of light, is 3 times 10 to the 8 meters per second, and we're squaring that. And pi, and the radius of the particle is 2 micrometers. It's 2 into 10 minus 6 meters squared. All right, so this is 10 to the minus 12. Okay, let's take care of powers of 10. This is 10 minus 9, so that's 10 minus 16, and that's 10 to the 16, so that cancels that. You get 10 to the minus 12, which will bring to the top. So E max square did I do this right? Oh, no, hang on a second. That's squared. Okay, so this is 9 minus 16. Oh, yeah, that's 16. Okay. So this is 10 minus 12. That comes to the top. 10 to the 12. 10 times 0.3 times 2 into 4 pi into 9 divided by 4 pi. So that's 3 into 6, 6 times 9, 54. So E max equal to 7.35 into 10 to the 6 volts per meter. And let's look at the, so you saw that in one of the previous problems, the strength of the electric field, the amplitude of the electric field of sunlight at Earth is 1000 volt per meter. So this intensity is 1000 times greater. Okay, so you're much closer to the sun where this light beam is stopping that particle. Okay. So you have to be much closer to the sun. Okay, this problem says, what is the frequency of a 193 nanometer ultraviolet radiation used in laser eye surgery? Okay, so C equal to frequency times lambda. Frequency is C over lambda. C is 3 times 10 to the 8 meters per second. And the wavelength is 193 193 nanometers, 10 to the minus 9 meters. So that's 10 to the 17, and we'll make it 300, so 10 to the 15 hertz, and 300 divided by 193. 1.55 into that. So that's the frequency of that light, the laser that's used. So it's a UV laser that's used in the LASIK surgery. And then assuming the accuracy with which this electromagnetic radiation can ablate, reshape the cornea is directly proportional to the wavelength. All right, so the reason they are using an ultraviolet light is, see, that's the size, the smallest spot you can focus on is roughly equal to the wavelength. Okay, so again, like I said, in LASIK surgery, what they do is they will make an incision on your cornea, fold your cornea back, and then shine laser on it and burn off cells and reshape the cornea. Your cornea is what's responsible for 75% of the bending of light. Okay, and so by reshaping the cornea, you can make sure that the image is focused on the retina. Anyway, so you want to burn off as small spots as possible, and that's why they're using this UV radiation, okay, whose wavelength is as small as possible. Okay. How much more accurate can this UV radiation be than the shortest visible wavelength of light? Okay, so the shortest visible wavelength of light is blue light. Blue light, and that has a wavelength of 400 nanometers. Okay, so the UV light radiation divided by blue light is 193 nanometers divided by 400 nanometers. Okay, so it's almost twice as more accurate. Okay, its wavelength is half as much. So using this UV light, you're burning a spot that is 400, half that if you had used blue light. Okay. Again, the smaller the spots you burn, the more accurately you can shape your cornea, and that's the idea. Okay. All right, guys. So that